Welcome to our first screencast video of our distance learning for this year. And the topic is going to be, the overall topic is precipitation reactions, solubility, and net ionic equations. But as I started working these slides, I decided to split this into two videos because there's a fair amount of material here, and I've learned that people really won't watch these things for more than about 20 minutes at a pop. So the first video today barely even gets us to precipitation reactions because what I want you to do is learn how to write ionic compounds as their dissociated ions. And so to see what I mean by that, let's move on. So here are a couple of images that were in a previous slide presentation. And this is the first thing I want you to think about up front is that when ionic compounds dissolve in water, the ions separate from each other and they're surrounded by water molecules. Now, this is the last time you're going to see an image in which the water molecules are around the ions. But I want you the point I'm trying to make here, and I'll make it more explicitly on the next slide, is that when I dissolve a compound, say sodium chloride in water, its ions split apart into hydrated sodium ions and hydrated chloride ions. This process of water surrounding ions is known as hydration. The critical thing to understand here is what I just said on the previous slide. When an ionic compound dissolves in water, the ions separate from each other. Okay, so I can show you here a picture of a sodium chloride crystal. So if we were talking about solid sodium chloride, it would look like this. It would just be this giant crystal lattice of sodium ions and chloride ions. What does sodium chloride look like dissolved in water? It does not, it does not form sodium chloride molecules in which you have a this just breaks up into a bunch of molecules in which there's a sodium and a chloride bound together. That is not what happens. What does happen is that all the ions split apart. So this is solid sodium chloride. Aqueous sodium chloride is not sodium chloride molecules floating around in solution. There's no such thing. What it is sodium ions and chloride ions floating around in solution. And so we can write that. Well, first of all, let's just this is just kind of a repeat of what was on the previous page. Aqueous sodium chloride consists of if it's a mole of sodium chloride, consists of a mole of sodium atoms and a mole of sodium ions and a mole of chloride ions, all separated from each other. The sodium's separated from the chlorides, and within that mole of sodiums, all of the ions separated from each other. We know there's one of each because in the formula for sodium chloride, the subscripts are each one. There's one sodium, one chloride, therefore I get 1 mole of sodium, 1 mole of chloride. If I have something that has subscripts in it other than one, then I don't get 1 mole of each. A mole of calcium chloride, because the formula here is CaCl2, a mole of calcium chloride gives me 1 mole of calcium ions, because the subscript there is 1, but 2 moles of chloride ions, because the subscript there is 2. And so the key skill that we want to be able to develop out of all of this is the ability to write the formula of an aqueous ionic compound in its dissociated ions. And so what do I mean by that? Well, if I have a mole of aqueous sodium chloride, if I take a mole of sodium chloride and I dissolve it in water, I could write NaCl aqueous. But what really exists in solution is what we call this dissociated form, in which it has dissociated into a mole of sodium cations and a mole of chloride anions. If I have a mole of calcium chloride, okay, remember back here, that calcium chloride gives me 1 mole of calcium, but 2 moles of chloride because the subscript is 2. Okay. Now I write that as 1 mole of calcium chloride gives me 1 mole of calcium ions plus 2 moles of chloride ions. Okay. And if I extend this out, say, to sodium carbonate, a 1 mole of sodium carbonate, when dissolved in water, actually dissociates to give me 2 moles of sodium, because the sodium has a subscript of 2, and 1 mole of carbonate. Remember, carbonate is a polyatomic ion, so it all sticks together. And so what I really want you to see here is that subscripts are becoming coefficients. When I take that thing and write it as its dissociated ions, the subscripts here, 1 and 1, become the coefficients, 1 and 1. Here the subscripts are 1 and 2, so now the coefficients are 1 and 2. Here the subscripts are 2 and 1, remembering again that carbonate's a polyatomic ion. So here the coefficients are 2 and 1. Okay, well, here's an opportunity for you to try a practice problem. So I have written down the formula of 4 compounds here: potassium bromide, sodium phosphate, magnesium bromide, aluminum nitrate. I'm indicating that they're aqueous, which means that they are dissolved in water. Your job is to pause the video for just a second, and in the same fashion that I was doing this, converting the total compound formula into its dissociated ions, go ahead and rewrite each of these aqueous formulas as their dissociated ions. So you can go ahead and turn the video off and try that. And when you've got answers, you can turn it back on. All right, how did you do? Here are the answers. In the case of bromide, because both of the coefficients are 1, I get 1 mole of potassium ions and 1 mole of bromide ions. In the case of sodium phosphate, because the coefficients here are 3 and 1, once again, I'm asking you to recall that phosphate is a polyatomic ion, so it does not break up. So it's 3 moles of sodium, 1 mole of phosphate, 3 moles of sodium ions, 1 mole of phosphate ions. Magnesium bromide, the coefficients are 1 and 2, so I get 1 mole of magnesium, then I get 2 moles of bromide. And then aluminum nitrate, because the coefficients here are 1 and 3, I get 1 mole of aluminum and 3 moles of nitrate ions. Well, if you feel confident that you have mastered that skill, then let's go on to the next thing, and that is we need to be able to also simultaneously, um, dissociate an ionic compound into its ions, but also handle a coefficient that might be in front of that substance. Remember, when we balance equations, we sometimes put coefficients in front of the substance itself. Here, none of these substances have coefficients in front of them. It's just 1 mole of each, and so you just use the subscripts to figure out how many moles of each ion you have. But you can appreciate that in the process of balancing an equation, you might have to put a 2 in front of a sodium chloride, or a 3 or a 4, in order to get that equation to balance. And so you need to be able to manipulate that coefficient when we are rewriting that compound, not as just an intact aqueous compound, but as its ions. And so what you're simply going to do is multiply the coefficient by the subscript of each ion. Coefficient of 2, subscript of sodium is 1, so I get 2 moles of sodium ions. Coefficient is 2, subscript of chloride is 1, so I get 2 moles of chloride ions. Now let's take a look at calcium chloride. The coefficient is 3, the subscript of calcium is 1, so I get 3 moles of calcium ions. The coefficient is 3, the subscript of chloride is 2. I multiply those together, I get 6 moles of chloride ions. Each mole of calcium chloride gives me 2 moles of chloride, but I've got 3 moles of calcium chloride. So I've got 6 moles of chloride. There goes Rufus, doing his Parky thing. And let's try one more, sodium carbonate. Here the coefficient is 2. The subscript of sodium is 2, so I multiply 2 by 2 to get 4 moles of sodium. And I multiply the coefficient of 2. Once again, this is carbonate of polyatomic ions, so its overall subscript is 1. 2 times 1 gives me 2 moles of carbonate ion. So what I've been trying to show you here is that to do this, we multiply the coefficients by the subscripts to get the ultimate coefficient for the ion that we are considering. So for each ion, just let's pick out chloride. Let's pick out chloride here. We're thinking just strictly about the chloride. 3 moles of compound times 2 moles of chloride per mole of compound gives me 6 moles of chloride. All right, so go ahead. Now here is a set of practice problems that you can try. So once again, in this case, it's the same for compounds that I had given you earlier, but now I have put coefficients in front of them. So go ahead and switch off the video and take however much time you need to dissociate 6 moles of KBr into its ions, dissociate 2 moles of sodium phosphate into its ions, dissociate 3 moles of magnesium bromide, dissociate 2 moles of aluminum nitrate. Go ahead and turn the video off now. All right, now let's see how you did this time. Once again, the key here is for each ion, you're multiplying the coefficient by the subscript. 6 times 1 for potassium gives me 6 moles of potassium. 6 times 1 for bromide gives me 6 moles of bromide. 2 times 3 for sodium ions gives me 6 moles of sodium. 2 times 1 for phosphate, remember phosphate's a polyatomic ion, gives me 2 moles of phosphate ion. 3 times 1 for magnesium here in magnesium bromide gives me 3 moles of magnesium ions. 3 times 2 for the bromide gives me 6 moles of bromide ions. 2 times 1 for the aluminum gives me 2 moles of aluminum ions. And 2 times 3 for the nitrate ions gives me 6 moles of nitrate ions. Okay, well, I hope you have sort of felt as if you kind of understand that skill, because now what I'm going to ask you to do is sort of the ultimate practice problem in which we are going to try to combine balancing an equation with then balancing an equation that includes all aqueous ionic compounds, and then combine that with then dissociating those ionic compounds into their individual ions. So first I'm going to ask you to balance the reaction below, and then to rewrite it not as intact compounds, but as dissociated ions. So here's the equation. Aluminum chloride, aqueous aluminum chloride plus aqueous calcium bromide gives me aqueous aluminum bromide plus aqueous calcium chloride. So take a minute to pause this if you'd like and balance the equation. All right, let's see how you did at equation balancing. Here is the balanced equation. So I'm going to put a 2 in front of both of the aluminum compounds and a 3 in front of both of the calcium compounds. You would figure that out. Presumably, if you got it correct, you know how to figure that out. I've got 3 chlorines on this side and 2 on that side, so I know that the least common multiple of that is 6. So I'm going to put a 2 here and a 3 there. I've got 2 bromines on this side and 3 bromines on this side. So once again, the least common multiple is 6. So I'm going to put a 3 here to give me 6 bromines and a 2 there to give me 6 bromines. And when I do that, I turn out getting also 2 aluminums on both sides and 3 calciums on both sides. All right, now comes the business of, we've only done these one compound at a time, of taking all 4 of these compounds now that we have balanced the equation and multiplying coefficients by subscripts to figure out exactly how many moles of each individual dissociated ion we have. So here comes the left-hand side of the equation. And you'll see in a second why I'm color coding these. 2 times 1 gives me 2 moles of aluminum ions. 2 times 3 gives me 6 moles of chloride ions. 3 times 2 gives me 3 moles of calcium ions. I'm sorry, 3 times 1 gives me 3 moles of calcium ions. 3 times 2 gives me 6 moles of bromide ions. Now let's do the right-hand side. 2 times 1 gives me 2 moles of aluminum ions. 2 times 3 gives me 6 moles of bromide ions. 3 times 1 gives me 3 moles of calcium ions. 3 times 2 gives me 6 moles of chloride ions. And now hopefully you can see what the point of the color coding is. If you've done this all correct, you'll see that I've got the same amount of everything on both sides of the equations. 2 aluminums, 6 chlorides, 3 calciums, 6 bromides. And of course, that's the whole point of balancing the equation, is to satisfy the law of conservation of mass. And just the color coding has shown you that we've done this correctly. Okay, let me just briefly talk about precipitation reactions, and then that will be the end of this specific video. A precipitation reaction is a specific type of double displacement reaction. And as you will recall, and we talked about this last week in class when we met physically in the same room, that a double displacement is a partner swap reaction. AB plus CD gives me AD plus CB. Because these are ionic compounds, the A and C are going to be cations, and B and D are going to be anions. And so you can't have the combination of AC or BD because an anion can't form a compound with another anion, and a cation can't form a compound with another cation. So you just swap the anions. A drops B and picks up D. C drops D and picks up B. And so in a precipitation reaction, these are all ionic compounds. In a precipitation reaction, both of your reactants are going to be soluble in water. But when you mix them together, you are going to produce one product that is not soluble in water. So let's just take a quick look at a video. And I believe this video actually comes out of the University of California at Berkeley, my alma mater. And so this is the classic precipitation reaction: sodium chloride plus silver nitrate. They are both soluble in water. In fact, let me just back that up for a second. Sodium chloride and silver nitrate are both water soluble. You can see these are both clear solutions. Now they are going to just show you the silver nitrate in solution. Now they're going to start dripping in the sodium chloride. And when we drip in the sodium chloride, immediately this white precipitate of silver chloride begins to form. That's because silver chloride is not soluble in water. And so one of the products is soluble in water and the other is not. Okay, so what did you just see? What you just saw was sodium chloride, which is water soluble, being added to silver nitrate, which is water soluble, to give two products. It's still a double displacement reaction, so there are two products. One of them is water soluble, sodium nitrate. The other one is not, silver chloride, so it precipitates out of solution. So we've talked about the solubility of ionic compounds in water. Most ionic compounds are water soluble, but not all ionic compounds are water soluble, and that's evidenced by the fact that you get a precipitation in this reaction. The precipitate is silver chloride. So in this particular case, sodium chloride, silver nitrate, and sodium nitrate are soluble in water, but silver chloride is not, and so it precipitates out of the solution. So when you mix sodium chloride and silver nitrate, as you saw in the video, a solid precipitate will form. All right, let's try one more practice problem just on this topic, and then I'll be through with this particular video. Let's try a different precipitation reaction. So in the one I'm about to show you, I'm asking you to determine which compounds are water soluble and which ones are not. So here is the reaction. Hydrogen bromide, when mixed with aqueous hydrogen bromide, when mixed with aqueous silver nitrate, gives a precipitate of silver bromide plus nitric acid, aqueous nitric acid. So the question is, which of these four substances are soluble in water and which of these four substances are not soluble in water? So the water soluble compounds are HBr, it's got an AQ next to it. Silver nitrate, it's got an AQ next to it. Nitric acid, it's got an AQ next to it. You didn't need to have known the name of that compound. And then silver bromide, because it's got an S, is a precipitate. It's a solid. It is going to precipitate out of the reaction. Okay, so that's the end of this video. In the next video, I am going to teach you how to recognize which of the products of a double displacement like reaction like this would not be soluble, and therefore predict what the precipitate is going to be. And then we're going to learn to write what are called net ionic equations. But for the time being, this video is complete. And so I will have, by the time this is posted, a in Veracross, I will also have a worksheet for you to work on associated with this video. Thanks for watching.